So we've already talked about a couple of these examples. Again, with NMR, we're talking about now interpreting NMR spectra, matching signals based on the splitting pattern and chemical shift, and then assigning the spectra to a molecule based on the structure. Right, and we also talked about a little bit of complex splitting. We talked about the doublet of doublets, and things like that. So these were our molecules that we looked at. I think we solved the spectrum for this one as well as the epoxide. And so now let's jump back in. I think we've already solved this one and this one. So now we have another spectrum right here. Let me move this out of the way too. All right. So this is another spectrum. And I think, so what, if somebody could tell me one thing that you remember from the last lecture. I know it was Friday, but tell me one thing that you remember from the last lecture about anything pertaining to solving these spectra.
You need to consider their chemical shifts to determine where they are.
The chemical shifts. Yeah, very important. I agree with that. And so we know that these two structures are out, right? Hold up. Sorry. Right. We know that these two structures are out. So you need to consider the chemical shift. What else do we need to consider? What about the number of signals? We need to think about that too. Is that right?
Yes.
Yeah, because the number of signals is going to tell you how many different types of non-equivalent protons you have, right? So if we look at this spectrum, how many signals do we have? So let's count them. We say 1, 2, 3, 4, 5, 6, 7, including the OH proton. And that's exactly right. Right. So how many of these we know that this structure is out, and we know that the epoxide is out. How many signals would this molecule give based on what you see?
5.
Right. So 1, 2, 3, 4, 5. So so we can rule that out as well, right? So now we know that we can rule that out. So if we look at this molecule, the OH proton is already established. I need to pull my iPad up right quick, so hold tight. We know the OH proton is already known. And then we have 6 other signals that we need to assign, right? Which ones do you think are going to be the ones downfield?
The hydrogens on bromine and OH.
Okay, so the ones that are the ones that are near the bromine and the hydroxyl group. I agree with that. I agree with that. So let me pull up my iPad. All right. So let me move this. So this is our spectrum, is that right? And we agree that this is the molecule that is corresponding to. All right. So what's downfield? Somebody, can you repeat that? Somebody already said it, but you're saying that it'll be this hydrogen right here, right, and this one right here.
Mm-hmm.
Okay. All right. Now let's take this hydrogen, because they're both going to integrate. You can see that downfield, both signals integrate for one proton. The question is which is which, right? Because let's think about the green proton for a second. What should the splitting pattern be for that? If you look at that green proton. Right, think about, remember the neighbors have to be bonded to that carbon where the hydrogen is.
That would be 3.
Say again?
3.
3 neighbors, right? So the signal should be sorry for that. The signal should be a quartet. Is that right? Because N equals 3. Yes or no?
Yeah.
Now, what about the other one right here? What should that signal be? It's going to be the same thing, isn't it?
Mm-hmm.
So that's also going to be a quartet. So they're both quartets. So the question is which, right? We know that you can see here that this signal is 4 lines. Is that right?
Yes.
Mm-hmm. And this signal is also 4 lines. It just happens to be overlapping with the with the OH proton. All right. So they're both quartets. So which one do you think is furthest downfield? And think about what causes a proton or signal to shift downfield. What causes that?
Next to like an electronegative group.
Mm-hmm. So electronegative atom, electronegative functional group. So which atom is more electronegative, oxygen or bromine?
Oxygen.
Mm-hmm. So which signal do you think the orange proton corresponds to? I'm gonna say this one, right? And then the green one, I'm gonna say is this signal right here. Are we okay with that?
Mm-hmm.
Right? That orange proton should be further downfield because oxygen is more electronegative than bromine. So that proton should be the the magnetic field around it should be more de-shielded because it's next to a more electronegative atom. All right, we're okay with that?
Yeah.
All right, now let's look upfield, all the way upfield. All right, we got 2 triplets upfield. Look at the integration. You see the integration? They're both integrating for 3 hydrogens. Is that right? So what do you think those correspond to?
CH3.
CH3s.
The methyl groups, right? The methyl groups that are here on the end. Right? Those protons on those methyl groups are showing up down there. Can somebody tell me why they're triplets?
They have 2 neighbors.
That's exactly right. So let's say for this proton right here, N is 2, right? Because on the carbon next door to it, there are 2 hydrogens. So if N is 2, that means N plus 1 is 3. So it should be a triplet. All right. And then what about here? Same thing, right? So N is 2, N plus 1 is 3. Is that okay? So now which is which? What do you think? Which one is the one that's further? So they're both upfield, but which one you think is going to be more downfield than the other?
The one closest to OA.
Closer to oxygen. So the teal colored ones, right? So this is
Yeah.
going to be, let me see if I got a teal colored highlighter. And oh, wait a minute. Oh, I do. It's not perfect, but it's going to be this one, right? And then the other one is kind of, what is that? Fuchsia. I'll just use, yeah, I got that. The other one will be right here. That's purple. The other one will be there. Is that right? And so now let's look at the other signals, right? Both of those are, can you count the lines there? 1, 2, 3, 4, 5 lines. So both of those are pentets. Again, you got the same scenario. They both integrate for 2 protons, right? So what is that saying? That's saying that these CH2 groups here, those are the signals for those. Can somebody tell me why those two are not equivalent? I mean, they're both CH2s, right?
Mhm.
So why they're not equivalent?
It's not symmetric.
It's not symmetrical. So then even though it's a CH2, it's not the same, right? So you have to take that into account. That's why they show up as two different. I'm asking that question because I want to get your mind thinking about non-equivalence. That's how you're going to be able to tell how many signals you should see, right? If you understand non-equivalence, then you'll understand why those two things are showing up as two separate signals. All right. So now, which one do you think is which? And tell me why it's a pentet. So I need one person to tell me why it's a pentet. I need one person to tell me which one is the furthest downfield.
It's a pentet because they both have 4 neighbors.
Mm-hmm. So the
So
four neighbors are here, right? You got
right.
three on this carbon, sorry, and then one on that carbon. Is that right?
Right.
Okay. All right. Cool. I'm with you on that.
And then so you just do n+1 and
Right.
yeah, 4 is n. So it's equal to 5 for both.
Yeah. So let me erase that and cheat a little bit. So n is 4, n plus 1 is 5. Right. For both pentets.
Right.
Mm-hmm. Now, somebody tell me which one you expect to be further downfield.
The one closest to oxygen, the blue one.
Blue. So this one right here, right?
Mm-hmm.
That blue is bad. I need a darker blue. All right. And then so by default, the red one is going to be the furthest upfield. Is that right? So are you kind of understanding now, like how to interpret the spectra based on the structure? All right. If we had more time, we could actually like take the infrared and the mass spec and the NMR together and actually build the structure based on what's in the NMR, right? And we also need like an empirical formula, so we can know how many carbons, how many hydrogens, so on and so forth. And we can actually work backwards and take a spectrum and determine what the structure is. But we don't have time to do that. I wish we did, because that's a skill, and it takes a while to develop it. So any questions about this example right here?
Nope.
All right, so now we know what this spectrum is for, don't we? We know we ruled out all the other ones. We know it's not this, it's not this, and it's not this, so it's got to be this one. So now we need to assign these signals. All right, let's start upfield this time. All right. So you see the upfield shift at about